lecture is about synchronous motors. We will discuss the phasor diagrams of synchronous motors, the effects or the relationship between field excitation and load, and the effect of changing. So let's begin. Synchronous motors and synchronous alternators are exactly the same physical machines. There is absolutely no difference between the two. The construction of a synchronous motor is the same as all machines, whereby you have a stator and a rotor, and the rotor in the case of the synchronous motor, stator, rotor, and the rotor in the case of synchronous machine can be considered to be a magnetic field rotating inside another magnetic field. So you have the magnetic field from the rotor, and you have the magnetic field from the rotating magnetic field derived from applying a three-phase voltage to the windings of a stator. This is similar to the principle that is used in induction motors, whereby once you apply a three-phase voltage or a three-phase current is flowing through windings of that nature, they will naturally produce a rotating magnetic field. So in this case, you will have two magnetic fields interacting with each other. So what happens here is that the rotor experiences torque due to the interaction between the magnetic field in the field itself and the rotating magnetic field from the three-phase voltages. And what will happen is the rotor will physically try to catch up, in quotes, to the stator field, because the stator field, the rotating magnetic field, is rotating at the synchronous speed ns. And so the field will try to match that speed. Right? And what happens here is that the machine rotates at synchronous speed due to this principle of the rotor field matching its speed with the stator field. So similar to the synchronous alternator, the equivalent circuit for the synchronous motor consists of a terminal voltage, the internal generated voltage, and the various synchronous reactances that are present. So what you will end up having is your equation, which looks like that. Note the polarity of these elements. What you see is that the terminal voltage is supplying all these voltages, right? It has to supply the internal generated voltage, but in addition to that, you have the current IA moving in an opposite direction. So it goes from the terminal voltage from the supply to the internal generated voltage. And in most cases, the assumption is that it is operating on an infinite bus, which means that terminal voltage is constant and it is at 0 degrees. It is taken to have a polarity of 0 degrees. Okay, and in addition to that, you will then have your phasor diagram. And in addition to that, you will then have your phasor diagram that looks like something like that. So VT, which supplies EA and JZSIA. Okay. In most cases, we generally say JXSIA. In most cases, it is safe to assume that RA is negligible. Okay. At the same time, you will have your current IA, and notice the polarity of that current, whereby you will generally have a leading power factor for synchronous motors, and here is your power angle. So this is alternatively called your torque angle, and this is your power angle. Okay, that is power factor, and the internal generated voltage lags behind the terminal voltage within the synchronous motor. And because your synchronous motor has constant speed at all loads, the torque slip relationship will look like this. Right? And you'll find that for whatever torque is being supplied, the machine will always run at synchronous speed. And there are various torque points. So if your rated torque is there, you would then have a pull-out torque beyond which your machine will fall out of synchronization. And that is called slipping of poles. And so you have a speed regulation of 0 because you have no load and full load speeds being equal to each other. Yeah. You have a 0% speed regulation. So the rotor will always rotate at synchronous speed unless it is unable to do so because of falling out of synchronism with the machine. So let's look a bit more at the relationship between field excitation and load. So what you will find, this is the phasor diagram of your synchronous motor with terminal voltage over here and your internal generated voltage over here, and the relationship between the two, the synchronous reactance covering the difference between the two of them. Now, in the event of an increase in load, you will have your machine increasing if the load increases, that is, if you have a greater load that you need to rotate, the amount of torque that you need to generate increases. What that means is you will have a momentary slowing down of the speed of the motor while it catches up, and the current will increase. What will happen when the load is increased is that your internal generated voltage remains the same. Remember that we are only talking about increasing the load. We are not yet increasing or changing anything to do with excitation. Yeah, excitation is dependent on the field current, and at this point we are not changing anything to do with the field current. Let's just purely look at if the load increases. So you have your original load at that level and it increases to that amount. What you notice is it moves, the internal generated voltage retains its magnitude, but it moves along the locus, which is indicated here by this circular locus, down to the level where it is reduced. If we go and reduce, it will go on up to a point of 0 if it is supplying, that is a no load. When it is running at no load, that is the current that will be flowing. But if you go gradually increasing, the internal generated voltage will remain the same while the current flowing will increase, right? So this is what happens when you increase the load without changing field excitation. But what if we now change the field excitation? That is the flux that you have from its baseline. What happens is you change the value of the internal generated voltage, but it remains along the same power level. So this vertical axis represents your real power. That does not change. If you change the field current, you are simply changing the value of your internal generated voltage. So by varying the two, you can be able to change it to whatever level you would prefer. If you decrease the flux, that is at a negative increase, we'll then have your internal generated voltage reducing in magnitude, but at the same time, your current will try to keep up with the angle that is required. So your internal generated voltage will reduce in magnitude, but along the same horizontal line, so that the power remains the same. Okay, and these two will therefore give you whatever values you would possibly require. If you increase power, you can increase the power, while at the same time you reduce the magnitude of the internal generated voltage to whatever value you would prefer. So let's look at two possibilities. The first possibility is if you have a constant field and change in load. What we will observe is that EA in this particular case will have constant magnitude, which means that it will change its angle along a circular locus. And we will also see that current will increase as power increases. Okay. Number two, if we have a constant load but a change in excitation, what happens? You then have EA varying along a horizontal locus. Yeah, and in this particular case, IA will also increase as field current is increased. So it increases to match field current. So let's look at a couple of examples to illustrate these. Firstly, you have that motor, which has the details as explained. So we are asked to sketch the phasor diagram of the motor and find the values of IA and EA. So straight away we can draw the phasor diagram to look like that. VT, E, A, and J, X, S, I, A. The output power is given as, it's a 15 horsepower times 0.746 horsepower, which gives us 11.19 kilowatts. And the input is equal to output plus all the losses. Which is 11.19 plus the mechanical is 1.5. The core losses are 1 kilowatt. And there are no electric losses. So in total, this is 11.19 plus 1.5 plus 1 gives us 13.69. Next, we need to find the current in each phase. So this is given by input over 3 times Vt cos theta, which is 13.69 over 3 times the voltage was 28 times power factor, which was given as 0.8 leading. Now this is with the power factor of 0.8, so the angle is 36.87. So we have EA, which will be equal to so from this we can find J excess IA, which will be IA times J excess, which is J times 2.5 times 27.42 at an angle of 36.87. So we can draw it in as 68.55 an angle of 126.87 degrees. And we can then have EA, which is given by VT minus JXSIA, which is 208 minus 68.55 and 26.87, which is 255.09 at an angle of negative 12.4 degrees. So EA here will be at 12.4 degrees, and it is 255.1. And of course, we already got IA, which is 27.42 at an angle of 36.87. Okay. Next, as the power of the shaft is increased to 30 horsepower, the shaft will slow down momentarily, but then it will swing to a larger angle. So EA will shift, but to what extent? So let's look at after the shift. So P in will be now equal to 30 horsepower times 0.746 plus the same losses, which gives us 24.88 kilowatts. So using the same characteristics, we will now be able to get that the power in this particular case changes the angle. So your delta here will change to a new delta. Let's use a different color. It will change to a new delta. If we redraw the phasor diagram, you will notice that this is EA, that is JIXS, you will find that and that is delta, this being VT. You will notice that this component can be written as JXSIA cos theta, or it can be written as EA sine delta, which means that if our power equation is given by 3 VT IA cos theta, it can be equivalent to, this can be given as 3 VT IA cos theta XS over XS. Therefore, we can substitute this component with EA sine delta, which will in turn give us 3 VT EA sine delta over XS. In which case, we can be able to rearrange and find the value of delta. So delta would be given as sine delta is equal to input power times XS over 3 VT EA. Okay. And that in turn will then give us delta is equal to sine inverse of all of that, P in XS over 3 VT EA. So let's resolve that. It gives us sine inverse P in the second case is 24.88. XS has been given as 2.5. Over 3 times 208 times EA. The magnitude of EA remains the same, so it is 255.1 in this case. So sine inverse of 24.88 times 2.5 divided by 3 times 208 times 255.1. Gives us 23 degrees. So delta 2, which is what we're looking for. Delta 2 is 23 degrees. So that means that our EA is same magnitude, 255.1, but at an angle of negative 23 degrees, right? Because we are going from here to here, so it's negative 23 degrees. Okay. Likewise, IA can be found in the same way we did before, which was input over 3VT, but we can use the voltage equation. So it will be IA is equal to VT minus EA over JXS, which is 208 minus 255.1 at negative 23 over J 2.5. So 208 minus 255.1 at an angle of 23 divided by 2.5i. So this becomes IA is equal to 41.29 at an angle of 15 degrees. So you can then resolve your figures. So this was 255.1 at an angle of negative 23. This is JXS. IA, JXSIA is equal to IA times 2.5 J. Which is 103.2 at an angle of 105 degrees. That gives us our complete phasor diagram. What is the new motor power factor? Our power factor will be cosine of 15. our power factor. (0.966) leading, which we can represent here. IA2, let's just label this correctly. IA2 is 41.29 at an angle of 15 degrees. So let's look at a second example, the same motor, but with slightly different parameters. So in this case, we have the same conditions, but with the change of 0.85 power factor instead of 0.8, and it is supplying a 15 horsepower load. And we know that the field current IF is 4 amperes in the initial conditions. So if we have our initial phasor diagram, VT, it is still 208 volts, and we have EA, which is given by VT minus JXSIA. So before we can do this, let's look for IA. IA is given by input power over 3VT cos theta. It is given by the input, which is the load, which is 15. So it is a load which is 15 times 0.746 plus 1.5 plus 1.0, which is 15 times 0.746 plus 1.5 plus 1. That gives us 13.69 kilowatts. That's our input. So you can go back to IA. We have IA is equal to 13.69 over 3 times 208 times 0.85 in this case. So it's 25.81 amps. That's the magnitude. In order for us to find the angle, we'll do cos inverse of 0.8. Cos inverse of 0.85, which is 31.79. It is negative because it is a leading power factor. It is negative because it is a lagging power factor. So IA, which is 25.8 at 31.79. So now what is our EA? So we go back to EA, which is equal to VT minus xs times j, so that's 2.5j times 25.81 at an angle of 31.79. So it will be that 208 minus times 25.81 at an angle of 31.79. That gives us 182.44 at an angle of negative 17.5. So we can draw that in as well, 182 at negative 17. 182 at 17.5. So that gives us JXSIA, which we already had here, as 2.5 I times 25.81 into 31.7. Now part B. If the motor's flux is increased by 25%, sketch the new phasor diagram. So in this case, zoom in a bit. We try and get the new phasor diagram. When field current is increased by 25%, that means EA2 will become 1.25 times EA, the original. Yeah. So this becomes 1.25 times 182.446. So EA2 is equal to 228.05. Let's call it 228 volts. And the angle in this case, so delta 2. Now if we go back to this diagram, we know that the value of EA, which is here, is up a bit. So in this case, we know that this parameter, which represents P, will remain the same. So whatever happens to EA in this case, so EA has now become 228 volts. So it has increased from 182 to 228. Let's shift this slightly. So if it has now increased to 228, it means that it is remaining along the same point, but it is now EA2 at 228. And these, so you have delta, initial delta of 17.5 and a delta 2, which is now at a different angle, which means that these two values are equal. And this value is EA sine delta, and this one is EA sine delta 2. So those two are equal to each other. Yeah, so we obtain that by saying EA sine delta is equal to EA2 sine delta 2, which means delta 2 is equal to inverse sine of EA sine delta over EA2. This is given by sine inverse of EA, which was 182.446, times sine delta. Delta was 17.5 over EA2, which is 228. So sine inverse of 182.446 times sine negative 17.5 divided by 228, which gives us negative 13.92, which is delta 2. So therefore this angle is 13.92. Okay. Now we can obtain IA2 from the voltage equation, which will be VT minus EA2 over JXS. And this is 208 minus EA2, which was 228 at an angle of negative 13.92 over 2.5 J. And in this case, we have 208 minus 228 angle of 13.92 divided by 2.5 pi. This gives us 22.58 at an angle of 13.6 degrees. So 225 at an angle of 13.6 takes us into this territory. And if you find the cosine of that, you'll be able to get your power factor. So our power factor equals cos 13.6, which is 0.972 leading. So what has happened, as you have increased your flux, you have also increased the power factor. So you now have and JXS IA2 was 56.45 at an angle of 103.6 degrees, which was here, 56.45 degrees, 56.45. So that is our new phasor diagram with all the properties indicated. IA is shown, EA2 is there, and we have the power factor given as 0.97 leading.